I'd like to talk about plasma. One of the first things when we get introduced that we want to know when somebody says, "Hi, I'm writing a new language," is it the right language for me? Some of the usual questions are for this room is probably, well, is it pure functional programming, and is it strongly statically typed? And so for plasma, that's correct. So it is strong static, pure functional programming. It uses eager evaluation, and hopefully should help work well to interoperate with C. One of the next things we want to know is, why would you create a new language? I mean, we've already got some nice languages. Well, functional programming has this tendency to require caffeine. Thank you for setting me up. I really appreciate that. I like caffeine, I like coffee, but it shouldn't have to. And I think that's one of the points that I want to make. And whether it's plasma that ultimately, it's a very ambitious project, and I don't have a lot of resources to work on it, so it might not work. But hopefully something like this will, and will make functional programming a bit easier and a little less caffeine heavy and abstract sounding. And I keep on clicking the clicker. I don't know why it hasn't worked. So we've got a few goals in order to try and address that. One of the first goals is I'd like a blend between declarative and imperative programming, because I think that both have a lot to offer. We all know in this room, we're here today because functional and declarative programming gives you a lot of expressivity. Using fancy types, monads and applicatives and so on helps you express your problems easily. But at the same time, imperative programming has this thing called an array. Those are really helpful when you want to write fast algorithms. So, and I think that we should be looking at both paradigms for what things we can bring. So, and for me, it's the safety and guarantees that you get with strong static, pure functional programming. So, okay, that's still not working. I'll give up on that. Our second goal is some better, is simplicity. Now, we all know here probably that engineering something to be more simple will make it more reliable. There's less to go wrong. I think that when you're using a language, the simpler the language and the tools that you're using are, the easier it is to use them. Of course, the easier it is to learn them, but even once you're an expert, you'll find that that simplicity will help you use them more effectively. So some of the things we want to do for that are not use overly complex names, or category theory names. Call it mappable rather than functor. Mappable tells somebody who's not introduced to category theory what it actually does, what it's for. And somebody who does understand category still understands it. So, and the third goal is an emphasis on concurrency and parallelism. You can't have a modern language without addressing this some way. So I think that's a critical part. Of course, I want the usual concurrency operators. You want to be able to create tasks and have them communicate through channels and things like that. But some of the other things that are very important to me are deterministic parallelism, and that comes from using parallelism without concurrency, and you always get the same answer, and automatic parallelism. So, those were the dull slides. Now we get the interesting slides. So, hello world. The first thing that's a bit different, I'm mostly going to show you things that are different about plasma to what you already know. I'm not going to talk about type systems. Most people in the room are probably aware of what's available in functional programming with regards to type systems. So I want to show you the ways in which it's different. One of the ways is that it's statement-oriented. So we have two statements. That is working with the dot. We have No, that's completely not working. That's, we have two statements, print and return. And the print statement has this exclamation point, which tells us that it uses a resource. Which resource it uses, it will pick. The resource system will understand, and it will pick from the available resources in the head of the function. So this print uses I/O to print hello world, all very easy. So, and you can have multiple types of resources. So the resource system gives you multiple types of resources. Resources can either be used or observed. Observed is a read-only access to a resource. And that allows an optimizer compiler to reorder read-only uses of resources, which is handy and can help you as the programmer understand the model of what your program is doing. So you understand if there's been a side effect. I'm thinking of having resources form a hierarchy. So some resources will encompass others in a way. And other resources won't affect one another, and their code could be reordered relative to one another. And thanks for Peter for that idea. So we've more on statements. When statements involve assignments, the assignments work as you might expect, and it's the equivalent of let expressions, except that variables can't be shadowed. So I can't have let x and then within that let x to redefine it. That could lead to confusion, so I'd rather not have that. Where you do want to redefine something, or if you're a Mercury person, you would say use state variable notation. Hopefully I'll add that in the future. I haven't yet thought exactly how that will look, so I'm not going to show that, but hopefully there's some kind of idea for that. Statements, when they're part of conditional execution, like an if statement or pattern matching, when they assign variables, there's a few rules that you have to do to make sure that it's safe. If you use a variable that's produced by either of the parts of the if-then-else, if you use it afterwards, here, then it has to be defined on all the branches so that it's safe. If you don't use it afterwards, like x, then it can be local to that branch only, and you don't have to name it on the second branch. The exception to this is when a branch doesn't fall through. So whether it either returns an error or throws an exception. So then we don't need, in this case, to produce the file variable. So, and this gives you a very easy syntax for producing multiple values in a conditional expression. In a functional language, you'd normally have to tuple and untuple them. So in a more expression-oriented functional language, rather. You'd be tupling and untupling them or using something else, some other way to do that. So, but here, even the compiler won't be tupling them for you. So the compiler will put these on the stack rather than the heap. So I keep hoping that the clicker will work because I like it, but so I don't know what's going on. One of the very strange things, it's a functional language with loops. This is very different from a lot of other functional languages. There is one precedent, as far as I'm aware, of a functional language with loops, which is Sisal, so which we draw a lot of inspiration from. This is a simple map loop. It's equivalent to mapping f over the list of x's and producing y's. It's a little bit more wordy in this syntax, but we'll see that has a very good advantage once you get to more complex loops. So, like this one. So it's very easy to have multiple inputs and multiple outputs. And this is like, I think it's zip in Haskell, where you zip two lists together and they form a list of pairs, and then you work over that. So this is equivalent to zip and then map of the lists and produce 2 results. Oh, except that we've changed the type of one of them. These can be any kind of sequence. They might be lists, arrays, or streams, and we'll get to another one. And we'll show how that works. So yeah, you can build these like more sequences in your outputs, and you can have as many outputs and as many inputs as you like. Or the outputs can be reductions, like computing the maximum of all the x's, or the total of all the y's. So, and that can be, like, it's really quite expressive. So that's just habit. One of the other things that you ought to be able to do is have an accumulator so that one iteration of your loop can communicate to the next iteration. In this case, we're building the warnings 0 and warnings variables form an accumulator. Each iteration of the loop begins with warning 0 defined. It starts off as the empty list, which is given by the initial value here. And will produce, each iteration must produce the warnings variable, and that will be passed as warning 0 to the next iteration. You can also retrieve the final value of warnings and return it, so at the end of the loop. This warning's normally outside of the loop. You can't see the accumulator variable from inside. You have to make it an output. The other thing, like I said, these can be arrays, lists, or streams. They can also be generators. And generators will allow you to iterate over any data structure you please, or anything you please. So in this case, we can have an infinite sequence of numbers, use them as identifiers, and adding the identifier to each thing and form a dictionary. So I think that using generators will be really quite expressive. It also allows you to define your own new generators to work with lists. The reductions are also generators that you can define. So I'm not certain of the interface for those yet. So on to concurrency. Well, we like having some, like a lot of control when it comes to concurrency. MVAR and semaphores give you a lot of control. With that control comes some great responsibility. But it's important to have it nevertheless, even if it makes things a little less safe. And these will use resources so that they are, so that you can see their effects within the declarative semantics. But you can use these to create other abstractions that are important in many situations. But of course, we'll add more powerful and arguably safer abstractions for concurrency. So some of my favorites are futures, just because they're so simple, and software transactional memory is another favorite. So we're also considering how we might implement a garbage collector that is aware of threads and will collect threads independently of one another, so that there's less stop the world kind of things. So there's still stop the world, but it just happens less. So software transactional memory might be the one of these that's unfamiliar. I hope that the other ones are familiar. If they're not, you can ask me. But this might be the novel one for a lot of people. This forms a whole atomic, says that all these have to execute or none of them. So they're atomic, it's a transaction. So, and it's very easy to use. So as you can read variables, you can update them. That should probably have a bang because that observes an effect, and I should update my slides. But these use the resource, the STM resource, to update the variables. If any of the variables are modified before the end of the transaction, before it closes, then the transaction will be aborted. It'll be rolled back, and the caller has the option of trying it again, or which is quite common, or aborting and doing something else. So, this is a lot safer than using multiple MVARs, which may not compose well. So it's these are composable, and they are, and you can use the STM variables in any order you like. You don't have to worry about deadlocks. Onto deterministic parallelism. We, like I said before, this is parallelism without concurrency. You don't spawn up threads. This means that the results you get out of your parallel execution will be the same every time, regardless of how it was parallelized, if there was parallelism at all. And separating it from concurrency is very important. Now, this has been done in imperative languages. They've got this thing called OpenMP, which allows you to add a pragma to your code and say, well, we'll parallelize. In this case, it'll parallelize the outer loop and render the image in each row in parallel in the image. And it'll probably chunk it up and do the right things, but you can control that as well if you need to. So we can add the same thing. Thanks again to Sisal for the inspiration for this. Sisal was a project at the Lawrence Livermore lab, and it used loops and arrays and these kinds of ideas. It didn't use generators. And along with some smart compilation technology, it managed to rival Fortran for performance. So, and thank you. And well, I can't say thank you because it's not my project, but at least it's really sad that it doesn't exist anymore. I want it to exist still because I think we lost something there. So in programming languages, we're always forgetting what's been done before, and I think this is one of those things that we've forgotten. So I think it's an important thing to draw inspiration from for performance and parallelism. So this parallel loop can also chunk up the loop and execute things in parallel. So, and this might not be the final syntax because I haven't written this stuff yet. So, like I said, Plasma is in a very early stage of development. So this is, like I said, very ambitious. So it's a talk about what I would like to do. So more than what I have done. You can also parallelize things involving a reduction. Normally, you might just loop over things and add them up, and you'd think, well, there's some accumulator there. I can't parallelize that. Well, this accumulator addition has this wonderful property of being associative and having a known identity element, which is 0. So it is easy to parallelize. You can break the list in half, add up the numbers in one half, starting at 0, and add up the numbers in the other half, and then add them together. It's easy. But provided that you know that your reduction thing has these properties. So we hope to make the user-defined reductions. I mean, all the reductions will be defined in the library or user code. Cheers. And allow users to define their own and get them running in parallel. So, there is, of course, other ways to parallelize this. If we can't parallelize the reduction for whatever reason, we can make it into a separate loop. So here, we just build up a list of y's and then parallelize that. So the parallelism is here over f. This works well if f is a costly thing, but addition is cheap, and addition is usually cheap. So, yeah, and the best way to parallelize some particular code depends upon that code and its data. Here's another way that the compiler might do it, or we might do it ourselves, is to create a stream between these loops. This way you still get the parallelism within this for loop, but you also get communication going between two tasks, and this loop can run in parallel with this one. So, yeah, and they communicate over a stream. Wise is highlighted because it's a bit unusual as well. It's produced here in this task. It gets its variable here and retrieves its variable here. It forms a future. The compiler can automatically, a compiler can automatically introduce a future and communicate the value between them. And Peter Wang, who was in the room, he can wave his hand if he likes, created this for Mercury. So, there's a smart guy. He knows how to automatically parallelize things. And he wrote some stuff about it. So, some of the things that he did, that I did, we figured out how to parallelize things when they were dependent, when they had a fair bit of communication between them. It went in only one direction. It wasn't bidirectional. And also how to handle some small cases of loops. What I'd like to do with Plasma, I think I can go further with this and add it for multiple types of loops and maybe some other patterns as well. And I think that's what's holding this kind of technology back. Oh yeah, this requires a little bit more research. So give this guy some money or some research grant. I'll wind up now. This is a labour of love. It's something I do in my spare time. I started about a year ago, which is when this photo was taken, about a year ago. Yes, I am in my pyjamas. This is what happens when you've got a new baby. You spend time in your pyjamas. And your mind falls out and you want to invent new programming languages. So this is how far we've gotten in about 12 months. We've got a bytecode interpreter. It uses token-based bytecode execution. I hope to improve that later and use something better. We've got enough stuff to get hello world and some basic calculations happening. What I'm currently working on is conditionals, and then I hope to do loops, continuations, and things like that. So if I've interested you and you think that Plasma, as opposed to in a language like Plasma, should exist, you might want to help. I think the best thing that anybody can do, that a lot of people might be able to do right now, is just let me know that you agree. That kind of encouragement actually goes a long way for motivation. But yes, follow us on Twitter, on the mailing lists. Try and check out the code and compile it if you're feeling brave. I haven't had anybody who can install Mercury have a problem. There's some notes in the to-do file if you're feeling super brave. So, and that's about it. I'll just shout out to Mercury, which Plasma is currently implemented in. I hope to make it self-hosting eventually. And I work for Yes Logic. We develop Prince XML, which is the wonderful package that formatted these slides. So it's a HTML and CSS to PDF conversion tool and helps you set out slides, among many other things. Thank you.
Oh, gosh. Thank you so much, Paul. We do have some time for questions, if anybody would like to ask any. I'll just bring the microphone to you.
It started working.
So that was really interesting.
Unless you want me to ask questions.
If you're in it, so for something, that's right. So if you're trying to parallelize a loop that draws on a generator and chunk it at the same time, you're going to have to do something like run the generator for your chunk size before kicking off the task. So your next chunk would have so you're getting chunks of sequential values from your generators. Are you planning to get the compiler smart enough to handle all of that sort of thing?
What I hope is that for many of the common loops where you're looping over a lists are super common, so we'll talk about that, is that the compiler will understand that natively and be able to do something smart aside from generators. I mean, some of the examples that I showed were equivalent to just using map. And so hopefully we can special case a lot of things like that. But sure, you could wrap the generator up in a mvar or something like that during compile time and share it, like pass it between the tasks or that kind of a thing. So I'm sure that there's transformations to handle it. And some will be smarter than others.
Cool. Any more questions? I'll come all the way up there. That's okay.
Thanks for the talk, very interesting. I just wonder if you could perhaps talk for a moment about this idea of resources and how that might be different from either monadic I/O or uniqueness types or other approaches. I realise you haven't got to that point in the implementation, but can you give us just some high-level ideas as to why you think that might be a promising way to model that effectful stuff?
It's more or less that I think that monads and uniqueness types aren't good at modelling that stuff. And so I'm hoping to find something that is. I'm not sure that resources will be it. So hopefully they are, and hopefully I pick a winner. If not, I might change the idea later, because as you said, it's not been implemented. I can always change it. So monads, my big problem with monads is that they're not composable. So even once you're an experienced developer, an experienced Haskell developer, and you understand monads inside and out, then composing them can still be a problem. And I think that one of the key properties of any piece of software is that it's composable. We write these things called subroutines so that we can call them as individual things. We use a stack so that we get reentrants, and those so function calls are composable. And I think that when you have some kind of effects, they ought to be. Now, uniqueness types are composable. Why I'd like to improve on uniqueness types, and that's what I'm used to from Mercury, why I'd like to improve on those is because they have a learning curve to get used to them. So I think that resources might be easier for new developers to pick up. And I didn't say it was in the slides, but I think that it's okay to have fancy things like uniqueness and things, but that you don't need them to write Hello World. And so you can gradually learn concepts as you go learning about functional programming or a specific language. So, yeah, I hope that helps. Anybody's welcome to come talk to me after if you don't find these answers or the slides satisfying. I'm happy to chat about this. I'd love to. So, yeah.
I think we have time for one more question. Yep.
Just sort of leading on from the last question, I'm working on a language called Pawns, which has a similar sort of thing to resources. I think there's a trade-off when you use resources, and the similar sort of concept in Pawns. It's more difficult to reuse code because the code tends to depend on particular resources rather than just having a big, more complicated type signature. So that's sort of a downside, but the upside is that things aren't dependent on the order of the different resources that you use. So if you've got a function which uses a few different resources, you don't have to decide the order in the type signature, and for any resource which gets modified, you don't have to sort of pass that in and return it and make the type signature more complicated. So I see that sort of approach as a bit of a compromise. And I think for things like I/O, it's definitely a winner. You probably don't want to overuse it though.
Yeah, I agree. Thank you, Lee. I had thought about your second comment that they form an unordered set and that you can define them in any order, and I like that property. I hadn't thought about the first point you made, that it does make a software component that uses resources is now tied to that resource. Yeah, I hadn't thought about that. I'd like to solve that as well, because obviously I want to solve everything. And I'll have a think about that and maybe we can chat later. But yeah, I agree with the point you raised. So, and Lee Nash's language pawns, everybody, is a very cool idea as well. He's created a language that is declarative but has pointer updates. So, so it's worth taking a look at as well. So, thank you.
Thank you.